Hello everyone and welcome to our presentation. I am Avinash Reddy and together with my teammates Mokshit and Gaurav Gautam, we are Group 6. Today we are excited to showcase our project, the City Route Finder. The main objective of this project is to solve a key logistical problem, finding the shortest and cheapest routes between cities. To do this efficiently, we have utilized the Floyd-Washer algorithm. In this video, we will break down exactly how the algorithm works, our solution, and let's dive in. Here is the roadmap of our today's presentation. We have designed this session to take you from the basic concept all the way to the final application. We will start by visualizing the problem with a flowchart and explaining the core logic behind the solution. Once the concept is clear, we will dive into the technical implementation with the algorithm and the pseudocode. Then we will showcase the actual project, the City Route Finder, in action. Finally, we will wrap up with the complexity analysis and conclusion. Now let's continue with the introduction. Initially introduce the project. At its core, the City Route Finder is designed to answer a simple question. What is the best way to get from city A to city B? To achieve this, we translate the real world into a mathematical model. We treat cities as nodes and roads as weighted edges, where the weight represents either distance, time, or cost. Using the Floyd-Warshall algorithm, a system calculates the most efficient path across the entire network. This allows users to optimize for what matters most to them, whether that is finding the shortest route to save time or the cheapest route to save money. It is a practical tool applicable to everything from personal travel planning to commercial logistics. Now let's continue with the code logic. Going on to the code logic, let's discuss the flowchart. The flowchart visualizes the logic flow of our application. We divided the process into three distinct phases. First is the setup. We start by inputting the number of cities and the distance or cost matrix. This establishes the network. Second is the calculation. This is the most crucial step. The system runs the Floyd-Warshall algorithm to process the entire network. It iterates through every possible path to find and store the optimal routes before the user even asks a question. Third is the user interaction. Because the heavy lifting is already done. When a user finally inputs a source and destination, the system can instantly retrieve and display the results, including the shortest path, the cheapest option, and the total cost. And finally, the algorithm will end. This is how the code works in the city route finder. Now let's look at the core logic behind the code and the algorithm. Let's dive into the code logic.
Now I'm going to explain about the core logic. How does it work? Like the slide explains about the mathematical brain of our project. If you look at the diagram at the bottom, like you can see the code decision the algorithm makes every single router. Imagine we are trying to go from a starting point I to a destination J. The algorithm introduces an intermediate stop K, and essentially is it faster to take a detour through K? Imagine if it compares the direct path against the combined distance I to k marked as 1 plus k to j marked as 2. If the detour is shorter than the route, we already know the algorithm updates by the matrix. So by repeating this simple check for every city, we guarantee that we find the absolute shortest path. Now, let's break down the algorithm into four simple steps. The first is initialization. We start by creating a matrix. We fill it with the direct distance we already know. Set the distance to itself as 0 and mark any unknown connections are infinity. Now, the second one is iteration. Like we set up the three nested loops. This allows us to look at every possible combination of source, a destination, and an intermediate point in between them. So the third one is like updating it. This is the core logic of this algorithm. Like we simply compare, is the path going through that intermediate point shorter than the current known path? If it was, then we should update the matrix with the new shorter distance. Now finally, once the loops all finish, the matrix is complete, so that it will giving us the shortest path between the every single pair of vertices. Like here is the pseudocode structure which puts the logic we just discussed it previous back in the code. The most important thing to focus on here is there is the three nested loops. Each variable in this the nested loops plays a specific role. Like k represents the intermediate vertex, think of as the true stopover point we are testing. I represent the source where the path starts, and j represents the destination, which means where the path ends. So by nesting these loops, the algorithm systematically asks for every possible starting point and ending point, is it faster to go through vertex k? Like logic we just discussed into actual code structure. Now the key takeaway here is the simplicity. As you can see, the entire algorithm relies on just three nested loops. The outer loops k is the most important. It iterates through every possible intermediate vertex. The inner loop I and j iterate through every source and destination pair. Now inside the loops we execute a single simple check: is the distance from I to j is shorter if you take a detour through k? So if the answer is yes, we update the matrix with that new lower value. Now, my friend Gaurav will continue the next topic.
Hello, I'm Gaurav Gautam. Now I'm going to explain our project. So let's go. Uh, this is our project, which is built using HTML, CSS, and JavaScript. Here is the correct logic for this project. This is basically a flat version logic. So let's run this. So this is basically a web page which name as city route finder. It's using for finding the shortest distance between any two cities. So let's simulate this. First, we load the cities. So click here. Now select the starting city. Let's select Delhi and select the destination city. Let's select Bangalore, and here you can select on the find route. So you can see here it's showing the distance between the Delhi to Bangalore, and it's also showing expenses and the number of routes, number of stops to go there. And here the city also shows the city visited. There see three cities like Delhi to Mumbai, Mumbai to Bangalore. So this is our basically using flat versal algorithm to finding shortest distance. We can also see here the distance matrix. This is basically a result of the solving the flat versal algorithm. And additionally, you can also remove and add the cities here according to your requirements. So this is our project, and this is a graph basically showing the routes, edges, or vertices, where vertices show the cities and edges showing the routes between the cities. So this is our project. Now move on to the next part, which is the time complexity part and the space complexity part. So first discuss the time complexity. This algorithm use the three nested loop. Basically, this is our main loop. This is for traversing and initializing. This is our basically flat versal algorithm logic. Here, three nested loop. It's give a it's run 0 to v and it's also run 0 to v. It's also run 0 to v, which finally gives a vq. So our time complexity comes for flat versal algorithm big of o v to the power 3. It means it has a cubic time complexity. This means that as the number of vertices increase, the running time grows very fast. Because of this, flat versal is best suited for a small or dense graph and not for very large graph. Now move on to the space complexity. So this algorithm maintains a v by v distance matrix where v rows, v columns, which store the v to the power 2 entries. Since the matrix contains v square entries, which gives a space complexity big of O v square. This is usually manageable for a medium-sized graph, but like time complexity, it also grows rapidly as the number of vertices increases. So now move on to its application and conclusion part. There are a lot of application where we can use this algorithm, like computer network system, urban traffic system. Urban traffic system that already we have seen, like our city route finder web page. And also it used in airline scheduling system, game development, like especially for how NPC path finding on grid maps, and also says social network analysis to calculate degree of separation between the users. You can also use in telecom routing. Many of the place where you can use this algorithm, many of the like application in a real life to use this. So as we can see, flat versal has a wide range of applications. Wherever we need shortest paths, we can use this algorithm. So now comes to its conclusion. In conclusion, the flat versal algorithm is a very powerful and elegant algorithm which is used for finding the shortest distance between the two places. Not like Dastra, it like covers all pairs. It find and search all pairs which is shortest. Like if you want to go A to B, so Dastra only find A to B short distance. Not like all pairs, but flat versal it search for A to C, C to B, like all pairs which is shortest. So it gives like optimal solutions and best paths. It is a simple, systematic, and works reliably with also with a negative edge weights. It has a only significant limitation is the its time complexity. We have already said it time complexity is big of O b to the power 3, which is very like not good for the like where number of vertices is very large. But for the graph of reasonable size, it performs extremely well. So because of its accuracy and flexibility and wide range of application, this algorithm is be one of the most important and beautiful algorithm in the graph theory. So thank you.